It has been so long since I've seen you. We are going to kind of do a review a bit beforehand. So, this is my explanation of the review that we do for solutions. So, hopefully, if you want to use this to study from, you can. So, just to clarify, that's not it. This will be in Schoology, and I'll put this along with some other things and the honors physics midterm exam info. Remember, that also goes over the info that we had. These are the solutions to this, which I uploaded at the beginning of break. So, with that being said, the first thing here is basically a vector problem. And so I said that the wind is going from west to east. This drone is going north to south. It's asking essentially where it should aim to get down in the least amount of time. So if you want to get down there in the least amount of time, you want to aim exactly in the direction that we wish to head. So in this particular case, that's going to be 100 meters divided by 12.5 meters per second. So that's going to be 8 seconds it takes to head down the field. It says across, but basically it's down the field. Now the next question's asking, well, if you want to end up due south without being blown off course, what direction should you aim? So in this case, you need to compensate for the wind. So I've drawn a triangle here. This is a vector diagram. So we know that the goal is to go directly south. The plane's going to have to aim west of south, and the wind is going to go from west to east. So when I draw it like that, I have 4 meters per second here, 12.5 meters per second over here. And when I do the trig, it's inverse sine, 4 over 12.5. So I get 18.7 degrees west of south, so 19 degrees west of south. You could also say 71 degrees south of west if you wanted to. Now it's going to ask how much time it should take. Well, now if you're not aiming due south, you're aiming somewhat west, this vertical part is going to be your resultant, and it's going to be a little lower than you had before. So I use Pythagorean theorem to get that. That's 11.8 meters per second. So now it's going to take a little longer, about 8.4 seconds to go down the field. This next one is both a vector problem and a conservation of momentum problem. So I've got two drones here. One's flying west to east, one's flying north to south. And it's asking if they stick together in a perfectly inelastic collision, determine the speed and direction of the wreckage just after that. So in this particular case, I'm going to calculate the momentum for each of them independently. This first one, 2 times 12.5, is 25 kilogram meters per second south. The second one, 3.5 times 8, 28 kilogram meters per second due east. If they stick together, then to find the resultant momentum, I use Pythagorean theorem. I get that, 37.5. And then I'm going to take that overall momentum and divide by the mass. So remember, P equals m times v is my overall momentum equation. So the key is momentum is conserved vectorially. It's a vector quantity. And so that's how you can find out the velocity. So this total momentum, which I got from Pythagorean theorem, 37.54. The mass, 5.5 kilograms. So I get this total speed of 6.8 meters per second. And when using inverse tangent to get the direction, I get 42 degrees south of east. Depending on how you drew it, you could have gotten 48 degrees east of south. Number 3, we did this lab really early in the quarter. So this is one where I ended up having a bunch of data here, plotted it out. Notice I showed you 2 points that I used to calculate the slope of the line. The slope of your line should come from the line, not necessarily data points, because data points involve some uncertainty, experimental errors, things like that. So at this point, this one was really weird, so I kind of ignored it. I got the slope of the line like this. So my slope was, this was 32 up here and 0, and this was 55 and 0. So 32 centimeters divided by 55 centimeters give me 0.58 centimeters per centimeter. So that's my slope, and this is my equation. Remember, dependent variable over here, independent variable over here. This would be a direct relationship because it's starting at 0 and it's a straight line. Inconsistency, you notice, and what would be a reason to cause this? So the inconsistency is you have an outlier, way outlier over here. You can make a decision of possible inconsistencies. This seems so far off, it's more than just like a measuring thing. So when I look at this, it seems like these two were flipped. So it seems like the bounce height and the drop height were put in the wrong columns. So at least for me, that was the most obvious thing. Is that an inconsistency or an error or an uncertainty? That looks like a mistake, so that's an error. It's not just natural variation in data. And what's one way students can reduce uncertainty? Multiple trials to collect additional data. So if we drop this from these heights, well, which would really be this height, like 3 times each, and we got the average bounce height, that would probably reduce our experimental uncertainty. This last one here, we've got cheese down a hill and then a Newton's second law problem. So it says assume that an errant cheese wheel, mass 7 kilograms, is sliding down a smooth frictionless incline, 34-degree angle from the horizontal. So draw the free body diagram. So I've got, and not components. I've got gravity here, and I've got the force of the hill or the normal force like that. I didn't show you the hill, so you could have drawn it up to the right. Doesn't really matter. So then it's asking about the net force acting on the cheese wheel. So here I redrew things, and so this gravitational force can be split up into the normal component and the parallel component. This is basically 34 degrees if this is 34 degrees. So the force of the hill and the normal component of gravity cancel out. So the net force is simply this parallel component. So it's just mg times the sine of theta. Why? Because I'm trying to get this side. This is opposite over hypotenuse. That mg is always our hypotenuse. So 7 times 10 newtons per kilogram, sine of 34 degrees is 39.1 newtons. I use 10 newtons per kilogram for all mine. If you wanted to use 9.8, your answers would be slightly different. I listed them here in a different color. Calculate the acceleration of the cheese wheel. Well, net force over mass of the system, 39.1 newtons over 7 kilograms. That gives me about 5.6 meters per second squared. Again, if you use 9.8, you'd have something like that. So the question is, why isn't this acceleration 10 meters per second squared if basically gravity is what's causing it to go down? And it's because gravity is not the only force acting on it. So we need to think about the fact that the hill is pushing up and at an angle, so we use the net force to determine the acceleration. Number 5 down here is another Newton's second law problem. It says assume you have a cart which has mass 1.5 kilograms being accelerated by a block, 0.5 kilograms. Assumes there's minimal friction. The pulley is both frictionless and massless. So in this case, draw the free body diagrams. I've got the table pushing up, gravity pulling down, tension of the string acting to the right. For this block, I have gravity acting down, tension acting up. These two tensions are an internal force, so they do not affect the acceleration of the whole system. And I've circled the system here. So to figure out the acceleration of the system, I'm going to use net force over mass of system. Well, the net force is gravity acting on the 0.5 kilogram mass, and the M system is M total, which is both the cart and the hanging mass of the block. So I have 5 newtons over 2 kilograms, and that's 2.5 meters per second squared. I did show you here how I got that gravity acting on the 0.5 kilograms, M times G, 0.5 kilograms times 10 newtons per kilogram. Again, if you use 9.8, your answers would differ a little bit. Now it's saying assume that the mass of this increases to 1 kilogram. Would the acceleration of the system double, more than double, or increase but less than double, or remain the same? So it's actually going to increase but less than double. While the net force will double, so we're looking at this equation here, the net force is going to go from 5 newtons to 10 newtons if this becomes 1 kilogram. The mass of the system also increases, and it increases from 2 kilograms to 2.5 kilograms. So instead of 10 newtons over 2 kilograms, which would give me double the acceleration, it's 10 newtons over 2.5 kilograms, which means my acceleration is now 4 meters per second squared. So a little bit sneaky here. I did a calculation, but the key here was this was a conceptual question. You need to think about this acceleration as a ratio. The numerator doubles, but the denominator increases some. So that's why overall the acceleration of the system increases but is not double. Hopefully these help and can get you refocused for your exam. Thanks.